This is a really quick intro to acceleration time graphs. You've already been working on velocity time graphs and position time graphs, so just wanted to get you to start thinking about acceleration time graphs and what they would mean and how they can show motion. And you've already started doing some calculations with acceleration when velocity was introduced to you, because you can use the slope of a velocity time graph to find acceleration. So you have seen this equation already, right? You had to use that to do the previous lesson. And I've just given you a quick sample here of 3 graphs, one acceleration time, one velocity time, and one position time, that shows essentially the same motion. So we're going to use mostly constant acceleration in grade 11. So what you're seeing here is a horizontal line on your acceleration time graph. So that tells you it's constant, right? It has a constant slope. So when you have motion that looks like that, it means you get a diagonal line on your velocity time graph, right? So we've got a diagonal line, and then you get a curved line on your position time graph because the velocity is changing. And in this case, we're going from something close to 0 down here to a higher positive number. So the slope of my dt goes from something close to 0 to a positive number as it changes. We'll just do a quick consideration of units and things you can find on an acceleration time graph. So we can directly find an acceleration, right? If I give you a time, so let's say I give you time here, and I want to know the acceleration, you would just go up, see where it hits the graph, and look to see what value that acceleration was, and you give me an answer. So our acceleration, we're going to just add some units to this here. The SI units for acceleration are meters per second squared, and let's just say this is forward to give it a direction. Okay, now what about the slope of acceleration time graphs? I wonder if that provides us with any information. So slope we know is rise over run. So rise would be this way, right? So rise would be delta A, so change in acceleration, which we know is in meters per second squared. And then we're dividing it by the run, so the run would be change in time. So that means we're in seconds. So we got meters per seconds divided by seconds, which would give us meters per seconds cubed, which is nothing that we're aware of and or care about. So actually the slope does not provide us with any information that we care about. Okay, and you can use the analysis of units to remind yourself of that if you ever get confused. Meters per second cubed means nothing to us, so we're never going to use the slope of acceleration. The only thing we notice here is that the slope is 0 in this case, because we have a horizontal line, and this is going to happen to us most of the time on an acceleration time graph in grade 11, because we want to have constant acceleration or uniform acceleration. Okay, we have uniform acceleration. And we're actually going to do a lab based on this, the class after this one. Okay, and now let's also consider the area under. So the area under here, we can consider the height, right? We're forming a square or a rectangle here. So you can see this square, if we look at the height, is a change in acceleration, right? So this is meters per second squared. And then we can look at the length of the box that's formed, right? So this is the length of the box that's formed. So that's in seconds. So we're multiplying by seconds, which means we've got per second squared on the bottom here and seconds on the top, which means we're left with just 1 second on the bottom. So we're left with meters per second. So this tells us that area under gives us a velocity. So we can use area to calculate velocity. And I apologize for my text message sound going off in the middle of that video. Maybe it provided you with some amusement. And hopefully you have a basic understanding of acceleration time graphs.